All right, good afternoon, class. So anyway, I guess one announcement for today is that I did want to get a homework assignment posted up before class today, but I had 1,000 things going on every day this week, so it's kind of a little bit of a challenge. But we'll get our next assignment posted up today after class, sometime around early afternoon or so. Um, so it'll be just mostly covering radix sort, bucket sort, and a few conceptual questions involving that. Something too bad. Hopefully the assignments this semester haven't been really too intense, but at least they kind of some scope or give you a chance to practice these problems. So anyway, so yes, for now, I'm going to just sort of recap, or not recap, but continue, but do a small recap from last time's stuff. So we're covering AVL trees and mostly how to remove from an AVL tree. So I'll recap a few of that. I'll go over the last two examples involving AVL trees, and then also have the proof on the height of AVL trees, and of course, then we'll go over the next topic. So let's go ahead and start a screen share. Let's go ahead and continue. So let's get my notes all together here. So pretty much for deleting from the AVL tree. So let's go over very first deletion I covered. So you have to find, say I want to delete 90, you have to find where 90 is. And since 90 has no children as a root, we just simply deallocate it, returning null. 85's right will be a null from this point on. Very simple example. So you end up getting this updated tree. And when I want to remove 12 from our AVL tree, well, we have to first find where 12 is. So we do our normal binary tree search. We find 12 is right there. And then basically we have to see, well, it only has one child. So we simply, or one subtree only. So you go ahead and deallocate 12 and return 7 up to the up to its parents. 25 will now point to 7 instead of 12. And that's really about it. So now once again, if any imbalances occur along the way, you have to rotate the tree as you move up the tree. So same idea like with insertion. If you remove something, there's a chance that an imbalance can happen. You would have to fix that imbalance potentially. So anyway, so let's go ahead and look at this example here. So kind of redo the example slightly. So here I want to remove 25 from my AVL tree. Well, in this case, well, we have two options. We can either replace this 25 with the in-order successor or the in-order predecessor. So in this example, I'll just go ahead and replace it with the in-order successor, which is really the smallest on the right subtree. So 30 is the successor of 25. So essentially all we have to do really, so I'm going to go ahead and maybe just, you already copied this earlier, so we'll have that tree there. So we're going to basically take 30 and we're going to remove it from the tree. Remove 30 like that. And then we're going to replace it with 25. That's sort of what's going to happen. So there's actually more going on there, but if I try to paraphrase every single aspect of this, it's going to be a little bit too much talking on this. So basically you have to take that successor and replace that 25 with it. Of course, update its height, which will now be 2. That's all you have to do in this case. And there was no imbalances to worry about over here. So I'm going to go ahead and put this here after moving 25. So I'll put this here. We chose this node. So we sort of replaced 25 with 30. That was about all we did. So pretty simple. Now, of course, if let's say 30 had subchildren or had a right child, you would move that up, and 35's left pointer would now point to 30's right subtree. So we know 30 cannot have a left subtree because it's in order successor. So if there was more elements to the left of 30, well then 30 wouldn't be the successor of 25. So We know 30 cannot have any left subtrees, but it could have a right subtree where we simply take that right subtree and assign that to 35's left pointer and replace 25 with 30. That's all you would do, so not too bad. So that's our resulting tree. And now let's go over the example of, well, what if we want to remove 25 again, but this time we're going to actually use the in-order predecessor instead. Let's cover that example. Use the exact same tree from before. Once again, I'm going to remove 25. So it's an alternative universe where in this case, we remove 25, but we pick the in-order predecessor this time. 25. We're going to choose the in-order predecessor. Really means just the largest on the left subtree. All right. So in this case, it's going to be 7. That's going to be largest on the left subtree because 7 has no right children. So the left of 25, you go as far right as possible, and 7 is the first we can go right. So this will be our predecessor, basically. Or sorry, predecessor. So once again, it can have a left child, but it can't have any right children. It's impossible because it's the furthest to the right. So we have to replace 7 with, so take 25 and replace 7 with that. So I'm going to go ahead and just copy this tree over here. And the result will be to take this 7 and replace 25 with it. Update the height to be 2. But we see here, we have a problem. Our tree at that level is imbalanced because 7's right subtree has a height of 1, and the left subtree has a height of -1, so we have a problem. So all the levels below 7 are fine, but we have an imbalance right here. So you have to fix this imbalance by doing some rotation. Well, we see here that, well, 7's right subtree is the bigger subtree, and that right subtree isn't larger, but it's not smaller. So we can, in fact, do a left rotation to fix this problem. As long as the right subtree is not the smaller of the two, we don't have to double rotate, although rotation wouldn't actually cause any problems here, but I'll just simplify this. But anyway, in this case, we can do one single left rotation by taking 35 lifted up. So we can actually end up doing the steps for rotation. So I'll just go ahead and sort of do this relatively quick. And 7 here, 5 over there. And what happens is, well, the 35 will get lifted up, 40 will fall below, then 7 goes over here, 7's right will be 30. That's just typical, that's left rotation. So what happens is, remember, the 7's right pointer now becomes pointing to 35's left. So the same code that involves with rotation. So 35 gets lifted up, 7 and 40 fall below, and 30 is going to get attached to 7's right side. Then we have 0, 1, 2, and now our tree is balanced after doing this deletion. So potentially you have to rotate after you do some deletion over here. So kind of want to wrap this up and not spend too much more time on this. But let's say, for example, what if I wanted to delete 50, given this tree over here? So maybe as just an exercise, maybe you want to practice this. So so you can go ahead and try to delete 50 from the following tree. So that's essentially what you have to do is, well, you have to sort of pick the successor or predecessor. So either a 40 or a 70 would actually replace the root. And you have to do rotations along the way, potentially. So let's say if you remove 40, let's say 40 gets lifted up, 40 becomes the new root now. Well, then we would have an imbalance of 35, 7, and 30. You have to double rotate this to fix that imbalance. If you take a 70 and you sort of take that 70 value and replace the root with 70, that would probably not cause any imbalances. So I won't cover that right now, but you can sort of think about how you would do this, but it wouldn't be too hard though. So that's basically how we do insertions and deletions. I'm not really sure how much I'm going to get really into this for homework and exams because it's really kind of a 302 topic. I know for sure many instructors cover this in 302, so this is kind of like a little recap. I wanted to, mention this or give an honorary mention to AVL trees just in case. So I'm going to go over a different example soon, and I wanted to at least kind of compare and contrast AVL trees with other search tree structures. So anyway, let's go over the proof of the height of an AVL tree. So it's pretty trivial. If the AVL tree is perfectly balanced, the height will be log of n. That's actually a very trivial case. So we don't really have to even show that. It's very easy to prove that. So if it's perfectly balanced, obviously it's going to be log of n height. We don't have to really do any kind of math on that. 302, you probably learned the math how to prove that. So anyway, let's go to the point where what's the worst case AVL tree? I want to go into the worst case scenario. And is this worst case scenario going to be balanced enough? So we know for an AVL tree, at every level except for the leaves, so the worst case scenario really is every level except the leaves, um, every left and right subtree height will have a difference of have a difference of exactly 1 at every single level. That is the worst case for an AVL tree. Except for the leaves, this is going to be the worst case. So having this worst case, is the height going to be pretty good? Will it still be logarithmic? So you probably might already know this, but let's go ahead and just sort of do a quick proof on this. So I use the following recurrence relation to show this. So we're going to have n of h, which h will be the height of our tree, n will be the amount of nodes for a tree of height h. And in the worst case, we're going to have, so put just a dash there. We're going to have n of h minus 1 plus n h minus 2 plus 1. We have the following recurrence relation. And I guess n of 0 would be 1, I suppose, but I'm not going to focus on the base case too much here, but there we go. So we have this recurrence relation. So we have the two subtrees. Here's our first subtree, and here's our other subtree of two subtrees. And they're going to have a difference of exactly 1. So one subtree will have a height that's 1 smaller than our current tree. Other one will have height minus 2. So the difference of the two subtrees will be off by exactly 1. And then plus 1 because every level has at least that one node, and plus the left subtree amount of nodes and the right subtree amount of nodes. So this recurrence relation perfectly models the worst case height for an AVL tree. So to solve this, I'm going to do a little bit of just messing around here with this example. So I'm going to go ahead and do the following. H be actually less than, so I'm going to go ahead and substitute this in. Substitute n h minus 1 with h minus 2. So this will be not exactly the same, but it will be roughly approximately. So then, so anyway, I'll explain this more afterwards, but we substitute this in. So we'll have still about the same approximate result. It won't be exactly the same, but similar-ish. So we're trying to do a substitution over here, and this amount will be less than the total number of nodes in our tree because we're replacing this larger tree with a smaller tree. So this count will be less than n of h. But anyway, now we have in a form where it's very simple to solve. So we can go ahead and say n of h is less than 2 times n h minus 2 plus 1. And this recurrence, if you kind of expand it, multiplying by 2, h minus 2 number of times. So we're going to have this 1 gets added up. So basically we're counting every time you multiply by 2, this recurrence. So it's 2 times 2 times 2 times 2. And we're doing this exactly h over 2 number of times. If it was h minus 1, we would actually multiply 2 h number of times. But since we're subtracting by 2, we're multiplying by 2 h over 2 number of times. So then the result will be n of h plus then 2 to the power h over 2 is the result. Now, of course, we can go ahead and solve this by taking the log of both sides. So we have log base 2 of n of h, here, so greater than h over 2. So h is less than 2 times log 2 instead h. So that means h has a max. H can never surpass 2 times log of 2. Now, of course, if we substitute an original formula, if we go ahead and put back h minus 1 for that subtree, it'll be exactly 2 times log 2 of n of h. N of h will be just n, basically. So the height can never be worse than 2 times log of n. Therefore, the height is going to be O of log n. I can even say theta, sure, let's put theta there. So this means that for an AVL tree, the height will always be log of n, no matter what. It can't be worse. It could be 2 times log of n, which is not bad, but it'll never be worse. It will never be asymptotically worse than log of n. So for the best case and the worst case, AVL tree is always log of n. So this is kind of a benefit. And of course, okay, fine. So the only real issue with AVL trees is that, well, we have the rotations. Rotations are sort of a constant operation. We have to just sort of modify 2 pointers and return a new pointer, a new node up to the parent, and that's it. So each rotation is constant in runtime. So doing extra work is not going to hurt the runtime because the height will always be logarithmic. And after we insert a new node, we do at most 2 rotations, and each rotation is constant in runtime. So insertion will take log n time, so will deletion, and so will find. So that's the benefit of it. The only downside is that we have to maintain a height variable in each node. And well, if n is very large, the number of digits will be log base. If using base 10, it'll be log base 10 of n. Number of digits will be needed, which I guess that's sort of, it wastes more memory, but that's the only sort of problem with AVL trees. So that sort of concludes AVL trees. So I'm not really sure how, I might go over some conceptual content on it. I'm not going to really maybe have you guys, maybe for a homework I can have you trace out some insertion and deletion, but I'm not really sure how much I want to get into this because it's really not a big topic for 477, but I wanted to at least kind of mention it, I guess. So next one is going to be a red-black tree. So I'm not sure if it's covered in 302. I know I don't cover it in 302. I know when I was a TA for 302 instructors, they didn't cover it. So some instructors might cover red-black trees, but I'm not sure how many though. So I have to like maybe in the future I'll probably just go and ask other 302 instructors and just sort of see what they're covering in their class. If I teach this class ever again, 477, I can try to see what they cover, so that way I can try to do my best to not overlap. But I still would cover this anyway because I still want to go over the search structures. So I'm trying to cover this new topic later on. I want to at least have us sort of understand these previous ones. So anyway, red-black trees. So it's also going to be a self-balancing binary search tree, just like an AVL tree. And the only thing we have to maintain is, well, what's going to happen is each node is is sort of assigned as red or black. So red black tree. So every node can be a red node or it could be a black node. That's basically the idea for red black trees. So we use these colors red and black, but really it's going to be a 0 or 1. So it's going to restore sort of a bit for each node, 0 or 1. So 0 could be black, 1 is red, or vice versa. It doesn't really matter, but we have sort of 0, 1 nodes, red, black, and I use red, black for the examples. So that's all we have to maintain, which is sort of already a little bit better than AVL tree, because AVL tree you have to maintain a height of every single node. Now, it's much more easier, conceptually much more obvious to see how AVL trees work. Red black trees are kind of, to me, kind of odd how they work. They do work, but they're sort of odd. But we have to only maintain just this one bit. So we have to use up as much memory as an AVL tree. That's like the real benefit of red black trees. So we have several properties that involve red black trees. So let's go ahead and just outline them. We have several properties. So the first one is, well, I guess here's the obvious one. Every node um, is red or black. That's, yeah, I mean, I guess that's written up here technically, but I guess I'll kind of formally define these properties. So here's our first property. So that's kind of like, well, that's sort of the idea. I mean, that would be shocking if it wasn't its first property. And then the root node is always a black node. So that's going to be that we always have to make sure the root is always going to be black. So we have to make sure of that. And then I guess this part is mostly just to make it sort of to handle. So this is mostly designed to sort of handle different cases or maintain the sort of the balance. Essentially, is kind of anyway every null node is a black node. This is just so in certain cases to maintain balance, it just sort of makes it easier to maintain the balance of our black trees. So a null node will be a black node. And then also, this is actually a pretty important property. So if a node is a red node, then both of its children black nodes. So if let's say a red node was a leaf node, well then the left and right would both be nil or null pointers, so then that would still maintain this property. So I guess a null node will be considered a black node just to um, handle these different cases. So we can't have basically back to back. We can't have a parent be red and a child be red. If we have that, we violate the red black tree order. And this one right here at the very end, I'll zoom out of this so we can write the whole thing down at the end. This very last property, you don't have to really constantly maintain it, but as a result of how we maintain red black trees, this property will be kind of, as a side effect, always will be maintained. So for each node, all simple paths from the node to the leaves contain same um, number nodes. Is actually a very important property for red-black trees. So this is actually going to maintain the balance. So what happens is at every single node, the left subtree, so if you look at just the black nodes, there'll be the same number on both sides at every single level. And that is going to actually maintain our balance. So for an AVL tree, you have to constantly, keep checking the left and right subtree heights and take a difference of them to see balance. But here, that last property, that's going to be really our balancing or the property that maintains balance. We don't have to actually constantly check that. But the way we actually construct a red-black tree, that last property will be just a side effect, or not side effect, but that's what we're trying to actually make sure we always have. We don't want to have sort of one side of our tree have more black nodes than the other. If we have that, then we have a chance that our tree might not be balanced. So this is going to really maintain the balance of our tree, essentially. So everything above it. So really, we're going to have to constantly do work to mostly preserve this. So pretty much, this sounds weird. No, so these concepts right here is what we're mostly going to be using. We're going to be sort of always making sure we're going to handle these cases. So these cases, we're going to have to actually write code or, trace out code to sort of handle these. Everything else is just sort of, the first property is implied. So the third property is also implied. And the last property is going to be a result of how we actually maintain everything in our tree. Okay, so basically, I'm not going to go over how a find operation works on red-black trees. It's the same as the find you would do for an AVL tree or a regular binary search tree. So doing a search is the same. So, I mean, I'll write it here just to write that here, but realistically, it will be the same as, so I'll just put this here for right now. Say find operation is the same as a find on any binary search tree. So nothing really surprising there. So runtime will depend on the height of the tree, as always, so nothing shocking there. Pretty straightforward in terms of how we do a search operation. Okay, so now insertion. So insertion operation, sorry. Well, it's going to be the same as a binary search tree. Insertion, we have to find where in our tree we have to insert an element. So that part's pretty simple. So for insertion, we have to we find vacant spot in tree, insert a new node. Now that's the same as always. So once we do that, then we have, just like AVL trees, we have to go ahead and fix the problem after we insert. So same idea here, we have to insert, we have to now fix the tree if one of these properties here is not maintained. So if you have some properties violated, we have to fix that property. Now typically, we have to make sure the only property we really have to check for, we have to make sure we're okay with, is making sure that the sort of black sort of nodes on both sides are the same. That's the only one we really have to actually do work to make sure that property is always maintained. So for example, now I guess I would use sort of, use black and red to draw this up, but I already have sort of a dark theme background. So I guess I'll use, I guess black will be will be white, I guess, and red will be red. And I could actually convert this one node to be sort of light themes, and it will be actually black and red nodes. But I think that wouldn't really be preferred because that's going to really be too bright for us. So let's go ahead and just sort of use that in this example. So we'll have sort of the following scenario. Let's say we have a black node over here, and then we'll have a red node over here as well. Like that. Now, also for insertion, I'll put this node over here. We always insert a red node into the tree. Then we can, of course, change the colors accordingly to maintain the red-black tree order. So right here, given the following tree, so this node, black node, could be the root or could be somewhere in our tree, somewhere more deeper in our tree. But let's say we had the following situation, and we insert a red node. So if we insert a red node over here, let's say it happens to go over here, let's say. So we always insert red node and say it goes right there. And we see right there we're violating our red-black tree order because we see here that we have a red parent and a red child, and we cannot have that. So what happens is we insert, remember how we always do insertions, we always insert over here, and we're going to return up to the parent. And then we're going to look at the grandparent at some point. So what happens is, as always, we have to return up the tree so after we're done inserting, we have to return elements or pointers up our tree. And at some point, we're going to look at the grandparent, and we see here grandparent notices that, well, it's a right child is red. So we have a red issue right there. So what happens is we have to check, I guess, the uncle or aunt. I can't think of a gender neutral word for that, but I'll just use the word uncle and aunt interchangeably. So for this node right here, we just inserted, its uncle/aunt is also a red node. And we can very easily find both because we're not going to check the error when a pointer is pointing to that child. So what happens as we turn up the tree, at some point, there'll be a pointer pointing to the grandparent. And the grandparent in constant time can find the child, the grandchild, and the sibling of the parent or the uncle or aunt. The grandparent can very quickly find them in constant time. So it notices that its grandchild is a red node, so is its child, and its other child, the aunt or uncle. So in this case over here, for this child node we just inserted, its aunt or uncle is red. If that's the situation, well, all we have to do is sort of do a color flip, basically. That's all we have to do. So the result in this case is going to just be the following. We're going to sort of change the grandparent to be red. This will be a black node. And now the order is, now everything is fine. If you notice over here, if you look at both sides of every node, the number of black nodes on left and right will be the same. So we know that for the very top level, for the root, if we take every simple path, we have 2 black nodes on the left side because we have this black node, and then its left child will be null, so we have 1, 2, or we have 1, 2. So that way we have 2 sort of black nodes on that side. On the right side, well, we have this one, so 1 and then 2, or we have 1, 2, or we have 1, 2. So we maintain the order. So as long as we have the same number of black nodes on both sides, we are fine. Now, of course, if let's say the red node was, the left child of, let's say, for example, I would have had it like this instead. Well, then it'd be the same idea, except that, we'd have the red over here. The same exact results. I don't want to show every single possible case, but that's basically happens there. And same idea, if I would have inserted red over here instead, somewhere on this side, well then the result would have been essentially this. So I don't want to show every case, but that's sort of the idea. So I'll show this one case over here just to kind of help us out with this. So this is sort of one scenario, but it can there's many different cases for this, but each of these cases would still, we have to sort of do this sort of color flip over here, because the idea was that we had the for a new child, so for a new insertion happened. Insertion, which is right here. The aunt is a red node. So we have to just do a color flip with the grandparent and the two children. Is it a color flip? It's grandparent, its children. In other words, actually, we just sort of flip the grandparents' color from red to black, and then we just set the two children to be the opposite color of the grandparent. That's all we had to do, really. So this was a very simple way to handle this problem. And now we have another case that could happen where, what if we have this situation? So I'll just zoom out so you can see all this. So now we have a case where, well, what if we don't have it where the aunt or uncle is red? Let's go ahead and look at that scenario right now. So hopefully you have all this written down. So I'm going to zoom back in so I can sort of draw a picture that goes sort of the scale. So now we have the situation. We're going to have sort of node right there. And so same as above, except now we're going to have it where as well. Of course, you have our red node right here, like this. So same as before, except that now it's going to be not black, red, red, but black, parent, left child is black, right child is red. And now we're going to insert another node. So we insert a red node right there. So you always insert red every single time. And we have this issue where we cannot have a red parent and a red child node. That violates the order. So in this situation, for the new insertion, we have, of course, so inserted node, then the aunt, cool, spell right now, is a black node, this situation. So we have, it's not red node this time. So doing a simple color flip is not going to fix this problem, because now we have a case where we actually have a different number of black nodes on one side over the other side. And we don't want that, because if we don't have the same number of black nodes on both sides, then we don't have a balanced tree anymore. Or, I mean, there's a chance that tree can become imbalanced. So you want to make sure, you want to always try to, so if we don't have the same number of black nodes on both sides, then we can't really guarantee our tree to be balanced. That's probably a better definition. And this doesn't guarantee, we may be unbalanced later on, essentially, is the idea. So when this happens, well, we have to do essentially a left rotation in the situation. So you have to left rotate to fix this problem. So rotation is same as with AVL trees, same idea. So remember, the grandparents' right pointer points to, so we would have it, so let's say right here, this is actually a null pointer. Set this to point over here, and set this one to point up there, using the same exact rotation sort of work, same idea. So what happens is, this red node is going to get lifted up. This right child will fall below. and we're going to have this formation. Now, it doesn't really appear to really fix the tree, but it's going to fix the issue with the sort of, how should I call this? The black nodes count on both sides will be the same. So after we do this rotation, then we have to do a color flip. So then I'm going to go ahead and draw this node over here. Draw this tree over here, sorry. We have to do color flips, so we have a black there, and then these will both be red. Actually, no, it's supposed to, hold on, maybe. So flip over here, rotation over there. It's up. Yeah, so that's going to be the result after that. So anyway, problem here is I think I might have my notes incorrect over here. How did I mistake? Hold on, because it's supposed to do a rotation over here. Red goes up, and we have black and black like that. Then you have to do a color flip afterwards. Color flip this to become black, and those to become red. I'll double check my notes on this. I do have my examples worked out, which they all come out correctly, but maybe I copied my notes down incorrectly, so I'll double check on this. We're supposed to have to rotate this for sure, and then you have to color flip. So I just don't know how, I think this doesn't come out the same though, because it's supposed to be the same on both sides. Over here, it looks like my notes, I might have made a mistake here. I can see. Because it's supposed to be, yeah, sort of one black node this way and two on this direction over there. So it's not that side. Anyway, I'll double check my notes on this later on, but I think there's a little mistake right there. I don't want to have to go through it right now, but I do have examples that I verify them as being correct. So I do have those for sure, but I don't know why my notes here, why I copied it wrong somewhere. But anyway, I'll update these and upload these to Canvas after class when I'm done with red black trees. But anyway, let's go ahead and just go over some examples actually instead. And these examples, I definitely verified those, so those definitely are correct, but I'm not sure what I did wrong over here though. Definitely red gets rotated up like that. Then we have to sort of recolor all of these. Anyway, let's do some examples instead on these. Let's go ahead and then sort of get an idea. So let's do that first. Let's do some examples. And then I'll just go ahead and I'll just double check my notes afterwards. So anyway, let's go ahead and insert, let's say we have our empty tree over here. I'm going to now insert 20 into this empty tree. So obviously we insert 20, well 20 has to be a red node. We always insert red into our tree, just like that. And then we have to just automatically change the color to be black because it's going to be a root node. So for root node, we have to make sure we sort of recolor this to be black node. So in the very first case, the very first insertion, we'll first insert red node into our tree. And automatically have to just sort of recolor the root node to black if it is red for whatever reason. So the first insertion was pretty simple. Let's go ahead and now insert 30 next. Insert 30. So I'm going to go ahead and just sort of insert 30 next. Well, we have our 20 node over there. Inserting 30 is going to put a red node to the right of 20, and we don't violate any we don't violate our red-black tree order because we have it where we don't have back-to-back red sort of nodes. That's the only thing we have to make sure we fix. We don't have this problem is our only restriction we have in this case. So then what's going to happen is we go into now, I guess I'll insert 10 next. So going back to our previous tree, we have 20 over here. We have 30. Inserting 10 would go right over here and does not violate our red-black tree order. So we're definitely just good right here. Now let's go ahead and insert 40. Now we'll have to actually do some more work than just simply insert. So let's go ahead and insert 40 next. Go ahead and copy our old tree. 20, 10, 30. That, and we insert 40 right over here into our tree. And we see here we have a problem. So when we go up to the very top level where we have our root, that's going to be the grandparent of 40, we see that the right child is red, and so is the grandchild of, or its grandchild, so the child of 30 is also red. So we see here that since the aunt/uncle 10 is also red, well, then a simple color flip is all we have to do to fix this red-black tree. So we take 20, make that into red, set these to be black nodes, and then so still remain red. And then of course we have to change the root 20 back to black because root node has to always be a black node. So I'll go ahead now and just do one more. So first, step by step, we have this, and then the result of this would be actually 20 and 30. Arrow for this as well. So we go from, so basically, we first insert 40, and we saw that we had this red issue. So I'll zoom out so we can see the entire picture. So we first inserted 40 into our original tree, so 40 went right there. We saw we had this issue because we had to, we can't really have it where we have red, back-to-back red nodes like this. We checked 40's aunt or uncle, which was a red node, 10. So we had to simply do a sort of a color flip with the grandparent and its two children. And then we have to color the root back because the root has to be always black and red-black tree. So that's all we had to do in this case. And now our height is maintained where the black node count on both sides is the same, which is kind of our goal. So now using this tree we have over here, we want to go ahead and now insert 35. Zoom out just a little bit so it'll be easier to this out. Insert 35. Go ahead and now just copy this picture. Okay, so in this case, we insert red node, and 35 would have to obviously go over here if we insert in our regular binary search tree order. And this will actually cause no problems, actually. Wait, never mind. 35 goes over here. My mistake. 35 would go over here. Okay, this actually does cause problems. 35 goes over there, and now we see an issue. The issue here is that, well, we have these back-to-back red sort of nodes. So in this case, we have to check, well, 35's aunt or uncle, well, it's nil, which means that we have sort of a black aunt or uncle. So we have to do rotation to fix this problem. Now, the problem here is that the right sort of child's left subtree has sort of a node. So we have to double rotate this potential tree because it's zigzag. So our first rotation is just to fix that zigzag. We're not going to do any sort of color swapping right here at all. on our first rotation, we're just going to simply rotate just to fix this potential zigzag. So, okay, fine. So go ahead and do that first. We have 20 above over here. We have 10, 30, and then we're going to have 35 there. And then we have 40 over there. We simply just do that rotation, just that right rotation first, to just basically fix that zigzag. And so we always want to avoid that zigzag with any binary search tree we do rotations. So now we have that zigzag problem solved, but the problem at hand is still here where we have a red parent and a red child, and the uncle or aunt of 40, it's a nil, which implies a nil is going to mean that we have sort of a black node for uncle or aunt. We have to do a left rotation to fix this imbalance. So over here, we're going to have 20. Five goes up. And 30 and 40 go below. So I'll circle these as well. Like that. So we fixed this zigzag problem first, and then we sort of rotate again to fix this imbalance. And now we have to do a color swap. Sort of circle this as well. We do a color swap now. So in this situation, so I'll draw the arrow that so the arrow, let's do like this, goes to the left. And then we're going to have another step, which we're going to basically have 20 at the top. Here it's red. Oops, I know you have here we're going to color swap these nodes. Yeah, it seems pretty simple. I don't know how in my notes how I messed that up, but that's really all there is to it. So after we do that rotation, we just do this sort of color swap. And we see here, everything is going to be still okay because in this situation, so the left side of 20, we have sort of one black node and then two, or we have that one, two, so we have two, so either path we take, we have two black nodes. On this side, we have this one black node, one, two, that one, or this one. So this path has two black nodes in it, two over here as well, and two over here as well. So this situation, every single possible path on both sides has the same number of black nodes. So everything is just fine. So it's still going to be balanced. As long as we have that property maintained, it'll be balanced. And really, this rotation and sort of recoloring is going to always make sure that that's preserved, where black node amount on both sides will always be the same, which will basically preserve our balance to this binary search tree. So after inserting 35, I'm going to now insert 5 into our tree. So I'm going to just copy this tree, draw all that. And let's go ahead and insert 5 now. That. So we have our tree over here. Inserting 5, well, 5 has to go over here. And inserting 5 is not going to cause any kind of problems because we don't have any violations. The only check we have to do is make sure that we look at the grandparents level, we don't have it where its child is red and then that child is also red. As long as you don't have that, then we're fine. Then all the properties will be maintained. And of course, making sure the root is black is very simple to check. We always have a pointer pointing to the root, so that's going to always be just fine. So let's go ahead now and taking this tree, which I'll go ahead and I'll copy this tree. Let's go ahead and now insert 2 into this tree. So in this case over here, I'm going to insert 2 into this existing tree. Insert 2, and I will simply same process again. So 2 has to appear on 5's left side, just like that. And we see here we have an issue because we have it where 5 is a red node, and shell is also a red node, so we have a problem. We have to fix this problem. So in this case, he would check the aunt or uncle of 2, which happens to be nil, so it's going to be a black node. So we have to rotate this tree to fix this problem. And since 10's left subtree is left contains more elements, we have to do a simple right rotation to fix this problem. We're almost done with the example. Yeah. So I don't know why that general sort of note I messed up on, because it seems like hard to get trees. But anyway, 20 over here, 35. So 40. And then we rotate. So then 5 is going to get lifted above. And the 2 will fall below, which was already there. And 10 falls below. After we do that, we simply just have to recolor. So 5 will be, so I'm going to go ahead and actually draw this over here. So then we're going to have, I'm going to maybe zoom out so we can see the entire thing. So what we're going to have is 20 is still going to be here, the root. We have 35. Expanding further so we can see all of it. 5, 30, 40. And then we're going to recolor, so 5 will be a black node. Then we're going to modify these both to be red. Simply have to rotate. So then the 10 to 5 goes up, and 5 will, we're going to recolor 5 to be, we're going to swap that color from red to black, and then sort of pick the opposite color for the 2 children. And then we have this situation. Now we have everything back in order. So really, a little bit simpler actually, maybe in AVL trees, because you have to constantly check the heights. You just have to just sort of check, make sure that at the grandparent level, we don't have back-to-back red nodes. That's all we have to do. So we're going to put this arrow over here. That's that. So let's do one more insertion. So this will be the last example. Let's insert 50 into this red-black tree. So I'm going to first copy this, insert 50, and then we can sort of end this example. Insert 50, and I will put that right over here. So inserting 50 is pretty, well, obviously pretty simple. 50 has to go over there. So we see once again, we have a back-to-back red issue, and the grandparent is 35, and the aunt or uncle of 50 is a red node. So a simple color swap is all we have to do. So I'm going to just, maybe I'll copy and paste this again. Um, 50 over here. Well, all I have to do basically is, since 35 is a grandparent, and 35 grandparent noticed that there's an issue, we're going to sort of have to recolor 35 to be a red node. And we want to have 30 and 40, we're going to sort of recolor these two to be black nodes. Everything's still okay. As long as number of black nodes on every single possible path is the same, then we're okay. So if you look at this example here, we have, so on the left side of 20 of a black node, and then 1 and 2, or 1 and 2, 2, 1 and 2. So we have 2 on this side. Right side we have 1, 2, 1, 2, 1, and 2, 1, and then 2, so 40, and then so every single possible path, we have the same number of black nodes on both paths. So everything is just fine. So I don't know how I messed up that earlier general sort of description of this because anyway, well, that's sort of the example. So I'm not really sure how much in depth I'll get with these for this class, but just I wanted to kind of mention essentially red-black trees as well. Let's go ahead and just go over sort of the proof for red-black trees. So let's go over what's the height going to be for red-black tree, essentially. That's what we want to go ahead and show next. Then I'll go ahead and talk a little bit about compare and contrast with AVL trees, and then we'll finally go over an actual search structure that sort of definitely has to be different from 302. I can't imagine this was covered in 302, this last one, but wrap this one up today. So I guess the proof of the height of a red tree. So basically here, so a few properties that we know we have to maintain is that the black node count is the same for every path. So we always have to maintain that, and doing those rotations and recoloring, color swapping is basically just to sort of make sure that we always maintain this. So ideally, because of this, the sort of the black black tree height is always the same on each side. So for every node, the left and right sort of black tree height will always be the same because we have the same number of black nodes on every possible simple path from that node to a leaf. So we have this always maintained. So really, the black tree, the black subtree of our tree is going to always be perfectly balanced. So the black subtree for the red-black tree is balanced. In other words, it has a height of O of log n. Just that, so basically that's going to be sort of our lower bound if you think about it, where the height will be at least log of n. Now, this is basically, if you have only just black nodes in our tree except for the leaves, then it'll be perfectly log of n. Now, in the worst possible case, well, in the worst case, on one side of the tree, we have red, black nodes alternating. If I spell it correctly, alternating. So we have black node, red node, black, red, like that. So that means on one side, it could be double the height than the other side, essentially. So we have our sort of our base that we know the black subtree height will be always log of n. And the worst case, we can't have back-to-back red nodes. So worst case, either on both sides or just one side. So on one side, or I guess even or both sides. We're going to have sort of this red and black alternating. So we have our base height of log of n, but it could get doubled because we could have a red node in between every single black node. So that means that the height will be twice the height of the black tree height. But the black tree height is going to be so the black subtree is going to always be a perfectly balanced binary search tree. So we can have at most 2 times the height of our black tree height, which implies that our height will be log of n. So the height of the red, black tree will be most twice the height of the black tree height. So we have our base height, and at most it can be twice as much, which means that the height will be O of log n, red black trees. So it has the same exact height, same logarithmic height as an AVL tree. So basically, for any type of application that involves binary search tree, there's no point to never not use an AVL tree or red black tree. They both have a height of log of n. So for a red black tree, as long as we make sure that we always have the same number of black nodes on both sides, then we'll have that very nice base height where we have that lower bound where we're going to have at least log n height, and then at most it can be twice as bad if we have red nodes alternating with the black, which it will make it twice as bad, but not asymptotically worse. So it will be log of n. So then, okay, what's the real difference with a red-black tree or an AVL tree? Well, here's sort of a few compare and contrasts. So an AVL tree AVL tree always maintains a very tight bound on the height. So long as if one side is off by 1 or off by more than 1, it'll balance immediately. Red-black trees, I don't think will basically always be as perfectly balanced, but balanced enough. I think there are examples that will cause it to be a little bit more imbalanced than AVL tree, but not worse logarithmically. But the real difference is that red-black trees, you only have to maintain just a Boolean 1 or 0 for red or black. So you don't have to maintain an actual integer value or some type of a number that stores the height of that tree. So you don't have to have that much space used because, think about it. If n is very large, then the height can be very big as well, and the height will be log of n, so we may have to have extra log n amount of memory will have to be used for every single node. Whereas for a red-black tree, you don't have to waste as much memory because storing a Boolean 1 or 0 for every single node is much better memory-wise, except that an AVL tree is a bit more simpler to maintain, especially when you want to delete from an AVL tree. It's very simple to delete. Red-black tree deletions is not that simple. It would take maybe a whole hour lecture to cover all that. So I don't want to really do that for 477, but it's a very big process though. So it's more steps, a bit more complicated, but the benefit is that we save memory with red-black trees instead of maintaining those heights accordingly. So the real difference is red-black trees save memory because you have to maintain a 1 or 0 for every node, but AVL tree is much more strict on the heights. So it has to be it's very strict in AVL tree because you can have the tree be a little bit lopsided or a little bit more on red-black trees, but still it's going to be relatively logarithmic in height, whereas AVL tree is much more tighter on the heights basically, but they'll both have the same log n height. So that's that. So I'll go over. So next time's topic, I believe, will be B trees according to our syllabus. So I'll discuss that next time. We may also have an exam review coming up soon. So our midterm will not be next week, but the week after. So week 8 is going to be our midterm. So let me go up to my calendar for a second here. So we're in week 6 right now. Week 7 will be this week of 5th and the 7th of October. So our exam would actually be on October 14th. So that's Thursday of the week 8. So October 14th will be our midterm. I'll make that announcement on Canvas as well. And I probably won't have an actual lockdown browser mode because I think that's sort of not preferred. So what's going to happen is I'll have a PDF posted, and it'll be just like a written exam. You have to write out on paper or use a writing pad or whatnot. And then you have to sort of upload that PDF up onto Canvas because I think for 477, multiple choice answers and all that is kind of silly. So I kind of want you to draw out some of the algorithms. So it might be a little bit hectic to try, do it on the Canvas quiz lockdown browser. So I'll make those all clear soon. So I'll probably have a review for the exam next Thursday. So you have a week to prepare for the exam. And the 14th will be our midterm. So that's the last little announcement. I'll make the announcement on Canvas as well. But I guess for right now, I guess that's it for today. So take care, you guys. Thanks for watching. Stay safe. Have an awesome weekend. And I'll see you on Tuesday.